Okay, so for those of you who attended the User Day conference, you'll find this presentation to be somewhat identical, actually. So if you saw the presentation last year, basically the conclusion we were looking at was programming to verbs is hard, doing it at all. Programming to verbs well is very hard. And what a lot of people just want is fast sockets. So this is one approach. SMCR and extended sockets are two other approaches. The general solution for RSOCKETS, just refresh your memory. It sits in user space. It's part of the RDMA CM, so it's part of that package. It does do kernel bypass. There is a preload library that's included. So the preload library is part of the lib RDMA CM package. It's built and installed separately. That allows some existing applications to run. So what I want to look at was basically what role was I searching for with RSOCKETS, kind of where is it at and what are its limitations. What approach I'm taking in terms of trying to get RSOCKET performance to be completely on par with native verb applications. So for some applications, it's actually on par or better depending on what the app is actually doing. But there is a gap there because of memory copies. And what are the future features? So what have I done since last year, since when I presented? And where do I see needs still existing for future development? Overall, there was very strong interest. So after I presented, several hundred people, or at least a couple hundred people actually went and looked at the video of the presentation last year. I received a lot of emails from RSOCKETS. And I even see RSOCKETS on slides that I don't create, so at least somebody likes it. Its primary focus originally was developed for basically MPI and HPC applications. So I've run it with MPI, Intel MPI and OSU MPI. I've run it with Hadoop. I've run it with VSFTP. That's one you probably don't actually want to use. But so I've tried it with several different applications, but starting with basically the HPC apps. Since then, I have added support for UDP, so it does do datagram support now. And it does provide a little bit of support for applications which call fork. So fork is really the problem child with RDMA, but it does do some support of apps which do that depending on what the apps are doing with the fork call. So goal going forward is to continue to increase the number of apps. Basically, this comes down to somebody needs to just run the app, tell me if it works or not, and if it doesn't, if they can tell me why it doesn't work. Typically, what I find with apps is it either makes a function call. So this is with existing apps. It makes a function call that I don't intercept with the preload library, or they set a socket option that I don't support yet. So I kind of do those basically as an as-need basis because I don't know how much the apps are really going to need. And the other goal is to decrease that performance gap, which I'll get to in just a couple minutes. And generally, RSOCKETS provides around 90–95% of the performance, basically raw performance for micro benchmarks relative to a native application. And my priority is performance. So this will be a little bit different than what, like, for example, the SMCR, which is more focused on compatibility. So I'm willing to give up some compatibility in order to maintain the performance it can provide. So this role, I also want to extend where I can take RSOCKETS in terms of both the performance and what applications it provides. When I look at other hardware interfaces, I actually had somebody come up to me, I guess on Sunday. Yes, I do have at least plans, I don't know when, to try to look at other hardware interfaces. So verbs is one hardware interface. Obviously, we looked at extending verbs. And do those extensions provide additional benefits that we can take advantage of? Or are there other optimizations, for example, PSN, which is a tag matching based interface. So that interface works best with Intel TrueScale hardware. And since I work for Intel, there's a push to have RSOCKETS work well with Intel hardware. So looking at all these other interfaces, can we support those as well? In terms of other devices, it does support InfiniBand, should support Rocky. iWarp support, I actually have the patches available. So I've written the iWarp support. What I don't have is iWarp hardware to test it. But the iWarp support, I'm expecting I'll have that available probably within days, if not at least a couple of weeks. It should be able to support iWork devices. And it has been extended to other platforms. So that actually wasn't my work. I helped somebody, but somebody else actually took the RSocket code, found it useful enough that they did port it to Windows, and it's part of the Windows Open Fabric stack. And that plugs in as basically a WinSock provider on Windows. So in terms of the performance, so I did add the RDMA specific options to set sock op, which allows me to control stuff like inline data size, size of the send queue, receive queue. Now I tried to pick defaults that worked well, basically provided very good latency, very good bandwidth, but minimized the memory footprint. Then I have some configuration files, so if an application can't actually make these calls, for example, using a preload library, an administrator can create these configuration files to override some of the defaults. And this has been useful for somebody tried to run RSockets over a WAN, and the latency was such that by the default, I only allocate like 128K buffer, and that wasn't enough to fill the bandwidth on a WAN. So they needed a much larger buffer in order to actually get the performance out of running this over a WAN. For natural extensions, so I mentioned some of this last year, adding some additional calls. These are specific to RSockets, so IO map, IO write, IO read. Last year I think I called these put and get. So I have implemented, for example, the IO map, unmap, and IO write calls. IO map basically is a memory registration type call. So that maps to a memory registration, but the user gets to specify essentially the R key or what address they want that buffer accessible through. And then the IO write call goes directly to that buffer. So using this, an application can basically register memory. They don't have to exchange any R keys. It's done automatically by the RSocket protocol. And the remote side just needs to be able to specify an address of a buffer, which could be known and basically compiled into the application in order to transfer data to it. IO read is another one. I haven't implemented that yet because IO read is really only useful if you have asynchronous IO, or it needs to be a completely blocking call. Which brings to the last piece is support for asynchronous IO. A lot of people for the past day or so have mentioned they really need asynchronous IO. However, Linux doesn't really define an asynchronous interface for sockets. So I expect at some point I'll get to that. It's just a matter of when and what that ends up looking like. So the top two are mostly done. The bottom one is still open. So in terms of the future, I need to have real keep alive support. iWork support I mentioned. In terms of UDP, I know that multicast is missing, but there's applications which desire multicast support. For compatibility, I want to be able to extend socket options as needed. Add this direct read capability. For example, even with blocking read, sorry, these screens end up being off, and it confuses me. So even with blocking IO read calls, I think something like Shemem may be able to take advantage of that. And I also need native IB addressing. So this is, for talk yesterday, the scalable SA is going to end up trying to use this, so we want to be able to have this native addressing and avoid scalability issues trying to always go through the IP stack to do the ARP protocols. For more full compatibility, we really need my opinion is we need a kernel-based solution. And we've had discussions with IBM, so I've had several discussions with IBM over several weeks about can we get, for example, RSockets and an SMCR to try to interoperate. So we have protocols that can support high performance, but also support full compatibility where needed. And that's just kind of highlighting the ones that hopefully will be available soon, at least those features. And then Jerry will come in here and step in for the SMCR. So what are the challenges? Obviously, the socket, my RSocket is not an FD, but a real socket is. So that means anything you pass an FD into, if you're running an existing app, I need to intercept that call. So dupe, fstat, those were calls I had to intercept based on applications, one of the apps I was trying to run. ePoll is a problem. So ePoll is fairly complex. So to get performance, I need to intercept all the ePoll calls and then basically create an entire user space implementation of what ePoll does. So For apps that do ePull, if they provide an option not to use ePull, that's my preference, but that's work I know that needs to be done. And then the other troublesome call is really change root. So this is like VSFTP uses a change root call. So that's a problem for the RDMA stack in general. It can't really easily support change root without some sort of changes to at least the RDMA CM portion of it. And then obviously fork I can do somewhat, depends on what the app is doing with the fork call. So, Jerry? Did I stay within 15 minutes?
PDF. So. That won't do the trick. Hang on just a second. There you go.
Okay, this.
Yep.
Okay.
That should work. There's a better pointer there.
Okay.
If you want it.
Okay.
That should move
Thank
you
you,
back and forth.
Appreciate it. Everyone, again, I'm Jerry Stevens with IBM. I've been working with Sean for the last 6 months on discussions of interoperability for the two solutions. I got just a quick disclaimer. The products that I'm discussing are not announced yet. Unfortunately, I can't talk about product deliverables or details. But I would like to talk to you about the solution itself and the architecture involved with that. And so basically, we have to step back for a moment and think a little differently for just a moment. So what we did on IBM and our platforms, we looked at RDMA and bringing it as a new technology, whereas you're looking at it from a different viewpoint. Our perspective was starting a little bit different and new. And when we looked at this, we looked at requirements that are very different. And yes, the very first requirement, of course, is performance. How much performance, how much does it need to improve before we can attract this category of customers? And of course, the first thing we have to look at is we really do need to provide full compatibility. So that's a challenge, as Sean just pointed out. There are some challenges with providing sockets over RDMA solution and providing complete compatibility. Also, customers are our customers are very interested in a set of TCP/IP existing network operational administration considerations. The number one consideration, of course, is IP security. And most of the large customers that we deal with are very strict about changing their IP topology at all. And so high availability is also very important to them. So if you're going to provide a solution, it has to provide resiliency. And load balancing is another particular problem for us. In all of our environments, we have multiple tiers. In every tier, there's a load balancer. And the load balancer can be a completely different vendor using slightly different architecture. If you're going to provide a connectivity solution, it has to be compatible with the load balancer. And then finally, it has to be something that's consumable to the users. And that just means that it needs to be almost turnkey. So most of the users do not like to get under the hood and change the knobs quite a bit. In fact, they get quite a bit of resistance for that. And then finally, we need something that works on both ends, interoperability. So the other platforms in our environment that we're going to communicate with, of course, both ends really need to be very consistent in terms of providing that interoperability. When we looked at the possible solutions to do this, of course, there was no such solution that existed. And so we created this thing called shared communications over RDMA. And I'm going to talk to you about the architecture and the protocol and what it does and how it addresses these requirements. And so on this chart, I show you an example of the concepts of shared memory communications. And basically, it's very similar to everything you've been hearing the last couple of days. It's the ability to share memory between two endpoints, and it has a producer-consumer model where the client server produces and consumes data. And we do that transparently to the socket applications. And we do, in this case, in this example, we do it over a wire. In this example, the focus primarily is on Rocky. And so in the amount of time I have here, I can only describe the concepts of the architecture. We have published an RFC that's available on the IETF. It's an informational RFC draft. You can go read that at that site and read about the details. And when you go look at it, you'll see that it's quite long RFC, but I would encourage you, if you are interested, to at least read the overview, and it'll take you through the low-level details of this concept. But basically, what we do is we transition from socket calls and directly post to write, and we produce data, and that ties exactly into the matching receive semantics on the other side, the target side. And so basically, as Sean pointed out, it is very efficient, and it's very close to, well, first of all, our reference is from existing performance. So in our comparisons, we look at standard Ethernet, standard TCP/IP, and how this works relative to that is fundamentally different. And so let me take you through just a little bit about how the protocol works. And basically what this is certainly RDMA focused on Rocky, but the SMCR is a hybrid solution. And what I mean by that is it uses the RDMA semantics, and it also relies on TCP/IP. And the way this works is that we allow the IP connection to go through. We do not use RDMA CM. There's no connection manager. TCP/IP is the connection manager. And basically what happens there is we'll negotiate switching out a band, keep the TCP connection active, and for all application flows, it's all now transparently accomplished with RDMA using the SMCR stack. And so they're independent stacks. You use the TCP/IP stack for connectivity, you use the RDMA flow processing for I/O processing. This SMCR protocol takes care of all the rendezvous, and fundamentally it borrows it from the TCP/IP processing, and it then exchanges data using RDMA write only. We do not use RDMA read, so it's just a push and a consume model. The TCP connection does stay active. There's several reasons for this. We have extensions in mind for the protocol, but this is primarily for keep alive security reasons, load balancer reasons, etc. We need this connection not only to go through, it needs to stay alive. And we have keep alives that flow if necessary. So this hybrid model, as you look at this, is why are you doing this? And I have to go backwards and we can touch on that again, but basically this model solves that long list of requirements that I just touched on. So here's an illustration of what this looks like. So what you'll see here is that there's an SMCR stack that sits beside the TCP/IP stack, and basically the connection sets up over the normal IP network. This only works, of course, in a LAN, a layer 2 reach. It doesn't work over the wide area network. But this IP connection sets up over doing the TCP handshake. We've introduced a new TCP experimental option 254 that communicates the TCP option SMCR. If both endpoints exchange that option, then the next step, we exchange a connection level flow that exchanges our RDMA credentials. It's very similar to SSL negotiation, if you're familiar with that. So basically, it's a three-way handshake, and then we have our own three-way handshake that follows. If that succeeds, then we proceed to use RDMA. If it does not, of course, we fall back to IP. And then what happens if it does succeed is the TCP connection will remain active, and then we will, from this point forward, we'll use RDMA for the exchange of user data across the RDMA fabric. And if this TCP connection were to terminate for any reason, we would break the RDMA connection. If the user would change an intrusion detection policy, an IP filter, anything that they would change that would disrupt that connection, it would, of course, disrupt the RDMA connection. So in effect, the IP connection controls the RDMA connection, which is now out of band. To the IP topology, it just appears that there's an IP connection that's fundamentally idle. So let's see if I have time here. Let me just touch on a couple things. So why did we do this? Again, it follows standard IP connection setup. And while that seems a bit trivial, but it does solve many of the security issues that I mentioned. It dynamically switches to RDMA. The application does not change at all. There's nothing for the application to change or to configure. Again, the TCP connection remains idle. It's for several reasons. It preserves critical operational network management characteristics of IP. So the key point there is this first bullet. There's no IP topology changes. You don't add IP addresses or remove them or change your IP subnets or adjust your networks. It also preserves your existing IP security model. So everything you have in the way of firewalls or zones or VLANs or IP filters, again, This is the number one bullet to our users is this one right here, is in terms of I can communicate using the optimized mode without changing my security model. It's also, this is very important, it must work with the connection load balancers. So that's very important, and I'll demonstrate how that works in just a moment. And then again, once you have this enabled, the operational and management day-to-day operations are essentially unchanged because you're managing your IP network, and the way we've integrated is that the RDMA semantics are displayable and the metrics are available with your TCP statistics. The way this works is that negotiation will create a reliably connected queue pair, and we in the architecture we'll call this an SMC link. And on this link, we will associate all the TCP connections between two peers on the same connection. And that could be a dozen connections, for example, or it could be hundreds. And the way we handle hundreds is we allow the SMC link to increase. We bond queue pairs together across physical unique paths. So at the transport layer, we create a link group, which can be a very large pipe. And it can be multiple connections. And so you can already see what this can do for you is we can move these connections around within the link group, and we can fail over, and we can load balance, and we can increase the bandwidth of that pipe using this architecture. And so the memory model, is the way this works, is every path has access to the same memory on both sides. So a sender can launch a write from any path, and the receiver does not need to know which path it took. And of course, you can stripe your data, et cetera. You can use the entire bandwidth of the path. And also, each operating system can independently manage its memory. So on one side, you could have, for example, a memory model that has very large buffers. On the other side, you could have much smaller buffers. In this example, the host on the left has 3 buffers, and the one on the right might have a 1 megabyte buffer, for example. So it allows you to independently manage your memory, but every path has an R key to access it. So I can write across any of the links within the link group. If we were to lose a path, an RNIC, an adapter, or a switch, again, we can detect the failure and move the TCP connections to another link within the link group, transparent to the applications. The application workloads are not disrupted. So high availability is provided as one of the requirements that must be there. This notion of a load balancer, most of you are probably familiar with different permutations of this, but here in this example I show a very simple of 2 tiers. The middle tier, that might be the app server or the web server, and the back end tier is the database server. And basically the way this works is that the middle tier will initiate a connection to a virtual IP address 2, which can be serviced by any of these back-end peers. And of course, the load balancer, based on various metrics, will direct that connection to one of the servers, and the IP connection now, the load balancer is aware of that connection for the life of it. And there also may be some security implementations within that load balancer as well. But nevertheless, the IP connection it goes through the load balancer, picks a target, could have been any of them, and then we go through our negotiation process that I just mentioned. So at that point in time, over the IP network, we'll negotiate RDMA. If it succeeds, we'll create a point-to-point connection out of band. And again, the IP connection is through the load balancer to the network administrator. It's aware of the connection. The load balancer is aware of it, but the data is exchanged directly out of band. And so once again, if the load balancer or the administrator terminates the connection, the RDMA connection is also terminated. Okay, so in summary, real quick, so the performance is the very key topic. The question is, if you can do this, how close can you mimic native performance? And unfortunately in this chart, I can't talk about, I don't have performance numbers yet. We do have performance numbers internally. We have preliminary numbers. They look very good. The performance is very impressive over, of course, native Ethernet. The IP processing, of course, the TCP IP stack is removed for data I/O exchange. So the transaction rate is very promising. Scalability CPU is also very good. I hope to be able to publish those numbers in the very near future. Socket transparency and full compliancy has been provided. So again, for our customers to enable that, it has to be completely compliant, which it is. Of course, it's Rocky compatible. We're looking at the other fabric types, but initially this is directed towards Rocky. So at this point, you do not change your application or you do not change your network. And then IP connection and related security features are preserved. This doesn't work across a firewall, of course, but it will allow you to communicate within a firewall or within a layer 2 network boundary. And again, it also preserves your IP ecosystem. So there's a couple talks here in the last day or so that talked about how enormous in the virtual switches and how enormous the data centers are growing. And this is real important to the users. So to help us speed up adoption, this is a key attribute of the fact that you don't have to change your IP topology. And again, transparency with load balancers. Resource sharing is very important for scalability, so a queue pair can be shared by many connections. And then if that queue pair is overloaded, we can spawn additional queue pairs, and we can create queue pairs across different physical paths. And virtual functions are also shared in this model as well. It also reserves the existing application task-ready model. So the memory that I showed you on that previous chart is managed by the solution itself. So the memory at each end, the applications, it's a store and forward model, and we're also looking at a zero copy model for a streaming workload as well. But the point is, with that memory model, we don't block an application at all. So basically, when it transmits, we copy and return to the application and allow the lower layers to handle the network processing. And again, from the network administration usability standpoint, there's really nothing to change in terms of other than enabling your new adapters. So fundamentally, you're enabling new hardware technology at your host, and you're using your existing network fabric, and you're using your existing network middleware. And so for today, really what I'm here for is Jim has invited me, as well as Paul, to make you aware of the solution, to seek feedback. If someone would like to talk to me, I'll be here to the end of the day. But we'd like to hear your thoughts on this. IBM's intentions are to make announcements in the near future about the solution. At that point in time, we can describe our performance attributes, which is really the #1 requirement. But certainly I would love to hear from you while I'm here if you have some thoughts on this. Real quick and backup, I don't know how I'm doing on time, but I just wanted to point out there's really 4 levels of the flow. It's a little bit more detail than what we can cover here, but the charts will be available on the website. But the first 2, of course, appear over the IP network. That's the IP handshake, the traditional TCP handshake. And then there's this connection level flow that we have that exchanges the RDMA credentials. Again, if #2 succeeds, we switch out of band and use RDMA. If it does not, then, of course, we just continue using IP. And then if we do, we have a set of primitives called link layer control commands that control that link in the link group itself, that allows us to dynamically add memory, add links, remove links, etc., to control that bigger pipe. And then, of course, data flows from the application over the queue pair itself. So the first 2 are over the IP network, and then 3 and 4, of course, are over the RDMA fabric. So it was pretty fast. I apologize for the pace, but hopefully you got the main concepts, and if you'd like to have some discussion about it. Sean and I, again, we've been discussing about how to make the 2 protocols work in terms of interoperability. That's ongoing work, and we hope we're optimistic that we'll get there. So,
thank you, Jerry.
thank you.
Yeah, so we have several minutes for questions. We're going to run 15 minutes behind what the agenda says.
I think I've seen this before, and I think I've said the same thing before. Can you show, give me some numbers that shows the performance benefit over a properly tuned TCP IP connection?
Yes, well, I don't have them with me today. I can't publish them. I hope to have them available, and we'll publish them in the next few months, 2 to 3 months, hopefully. But I can just tell you that it's an order of magnitude improvement. It's very, very impressive in terms of basically the socket calls are transferred immediately to the RDMA semantics. So there. Right. I guess we'll just have to show you the numbers, Christoph. I understand, and I understand that you have to see the differences. But just as Sean pointed out, that there's differences with his process. It's very similar. The techniques are very similar, actually. And so, yeah, we'll hope to have some numbers for you very soon. Yes.
So, is there a kernel component to this, and do you foresee it being mainlined?
So, for the implementation that we have, it is a kernel. There is a kernel component. And as Sean also mentioned, we would need kernel help to get this solution into Linux, which we are pursuing. We have Linux implementation, a prototype working and functioning and tested, but we will need some help with the kernel to solve some of the aspects with the solution. Yes.
What's the license model that you're thinking of?
Well, right now we have the IBM part of it, and we'll have the Linux part of it. But basically we don't foresee any licensing fees. It would just be standard licensing. And in fact, we've already published the protocol. The architecture is all available. So we intend everything to be open as possible, right?
Any other questions? Okay, thank you
Okay,
very
thank
much,
you.
Jerry
Thank
and
you.
Sean.